Hello everyone, we'll start chapter 7, which is about functions, and section 7.1, which introduces the basic definitions about functions. We start with the definition of function. If you remember, we had defined a function when we were introducing relations in chapter 1. But now we define it in a more detailed way. Okay, so we say a function f from set x to set y is denoted like this. We say f column x, then a right arrow y, and f is a relation from x, which is called the domain of the function, to y, which is called the codomain of the function. That satisfies two different properties. The first one is that every element in x is related to some element in y, right? And the second one is that no element in x is related to more than one element in y. So if we are going to combine these two properties, we can say every element in x is related to one and only one element in y. Correct? So as it's mentioned here, given any element x in x, there is a unique element in y that is related to x by f, correct? And if we call this element y, then we say f sends x to y, or we say f maps x to y. These are equivalent statements. And this is how we write it symbolically. We say x, an arrow to the right, and y, or we write it in this way. And the unique element of which f sends x is denoted by this symbol, f of x, and the output of f for the input x, or the value of f at x, or the image of x under f. So all of these bold statements or bold expressions are substitutions for f of x. You can use any of them interchangeably. So the set of all values of f taken together is called the range of f, okay, or image of x under f. So this is the formal definition of range of a function. Range of a function f is this set, which is denoted by a set builder notation, is the set of all y's belongs to y, which is the codomain of the function, such that y is equal to f of x for some x in x. Or you can say there exists some x in x such that y is equal to f of x. Okay, so after defining the function, we define a few properties of function. First, we start with one-to-one functions. So let's assume that f is a function from set x, the domain of f, to set y, the codomain of f. So we call f a one-to-one function or an injective function if and only if for every pair of elements x1 and x2 in the domain, if f of x1 is equal to f of x2, then x1 is equal to x2, or should be equal to x2. Or equivalently, if you write the counterpositive of that conditional statement, if x1 is not equal to x2, then f of x1 is not equal to f of x2. So here this conditional statement is the contrapositive of this conditional statement. So they are logically equivalent, correct? You can use both forms as a definition of a one-to-one function. And this is the more symbolic way of writing this. We say f from x to y is one-to-one if and only if for every two elements x and y in X, if f of x is equal to f of x1 is equal to f of x2, then x1 and x2 must be equal. Now let's look at a few figures so that we can understand the concept of one-to-one function. What does one-to-one function mean? As you look at in this figure, the left figure, this is a function that is one-to-one. Why? Because this is a function because every element in the domain is related to one and only one element in the codomain. That's the definition of function. By why it is one-to-one, it's because there is no two elements in the domain that are mapped to one single element in the codomain. On the other hand, as you see in the right figure, the elements A and C are both mapped to W by function G, and that's why G is not one-to-one, but F is a one-to-one function. Again, please note that G is a function because every element in the domain is mapped to one and only one element in the codomain, but it is not a one-to-one function because there is two different elements in the domain that are both mapped to a single element in the codomain. That contradicts with the definition of one-to-one function, and that's why G is not a one-to-one function. Okay, so now let's see an example from the book, example 7.2.2, which is about proving or disproving that functions are one-to-one. Consider two functions f and g. F is from R to R, and G is from set of integers to set of integers. And F is defined by this equation. F of x is 4x minus 1 for every real number x, and G of n is equal to n square. Sorry, this is n square for every n belongs to the set of integers. And the question here is F one-to-one and is G one-to-one? You can either prove it or disprove it. If you want to disprove it, you have to give a counterexample. So for part A, consider x1 and x2 as two real numbers belongs to the domain of function f, which is the set of all real numbers, such that f of x1 is equal to f of x2, and by the definition of f, you can write f of x1 as 4x1 minus 1 and f of x2 as 4x2 minus 1, correct? By adding 1 to both sides of this equation, you'll get 4x1 equal to 4x2, and by dividing both sides by 4, we'll get x1 is equal to x2. So based on the definition of one-to-one function, we prove that f is a one-to-one function because from this equation, from f of x1 equal to f of x2, we conclude that this equation, which is x1 is equal to x2. That's how you prove the one-to-one property of a function. Now let's disprove the second part. The second part says, is G one-to-one? I'm going to show you that G of n is not a one-to-one function. G of n is n square. In order to disprove that a function is one-to-one, we need to give a counterexample. How? Let's see this example. I assume two different members of the domain. The domain was the set of real numbers, so I assume n1 equal to 2 and n2 is equal to negative 2. Now, by the definition of G, G of n1 is, which is G of 2, is 2 to power 2, is 2 square. 2 square is 4, and G of n2 is negative 2 square. And both G of 2 and G of negative 2 are equal to 4, correct? So G of n1 and G of n2 are equal, but n1 and n2 were not equal. One of them was 2, the other was negative 2. That's why we conclude that G is not one-to-one. So basically, in order to prove that G is not one-to-one, we give an example of two different elements in the domain, namely 2 and negative 2, such that they both map, they are both mapped to a single element in the codomain, which is 4, by function G. And that contradicts with the definition of one-to-one functions. That's why we have successfully disproved the one-to-one property of function G. Alright, so after defining one-to-one functions, here we define another property of function, which is onto functions. So let f be a function from X, from domain X to codomain Y. And based on this assumption, we call f onto if and only if given any element Y in the codomain Y, it is possible to find an element X in the domain with the property that Y is mapped or Y is equal to f of X. Means X is mapped to Y by the function f. So symbolically, we can say f is onto if and only if for every member of codomain there is a member of domain like X such that f of X is equal to that member of the codomain, which was Y. And if you negate this statement, you'll get the definition of not being onto. We say f is not onto if and only if, since the definition of onto was a universal statement, here we should have an existential statement in the negation of that statement. So f is not onto if and only if there is some element in the codomain like Y such that for every element of the domain like X, f of X is not equal to Y. In other words, there is no element in the domain that can be mapped to one element in the codomain. If you can find that one element, then you have disproved the onto-on property of a function. So again, in order to prove the onto-on property, we have to use direct proof, but in order to disprove that a function is one-to-one, I'm sorry, the function is onto, in order to disprove it, you need to give a counterexample, just like the one-to-one property that we showed an example in the previous slide. Okay, so let's see the a schematic view of onto functions. In this figure, we give you an example of an onto function. Function f is onto because every element in the codomain is equal to f of an element in the domain. It means that for every element in the codomain, there is an element like X that f of X is equal to that element of the codomain. So this is how an onto function should look like. However, in this figure, you see an example of a function that is not onto. Why? Because you can find some dots in the codomain like these two that have no, that are not related to any element of the domain. Okay, so there is no arrow pointed as pointed at these two dots. That's why the codomain is not totally covered, by F, and that's the definition of not being onto. So the function F in this figure is not onto because it does not cover all the members of the codomain. All right, so let's see an example of how to prove or disprove that functions are onto. Let's define f a function from R to R and h a function from Z to Z such that f is defined by this rule. F of x is equal to 4x minus 1 for every real number x, and h of n is equal to 4n minus 1 for every integer n. And the question is f onto? You can either prove it, or if you want to disprove it, you have to give a counterexample. And the same question for function h, is h onto? Either prove it or give a counterexample. In order to answer to part A, we are going to prove part A. So we say, let's assume that y is an arbitrarily chosen but particular element of the codomain, and now we must show that there is an x belongs to the real numbers such that f of x is equal to y. That's why we consider x as y plus 1 divided by 4. You will see later why we chose such real number. So if x is chosen as y plus 1 divided by 4, then you can see that f of x is equal to f of y plus 1 divided by 4 based on using substitution, because x was this. And then since we have a rule for f of x like this, you can simplify f of y plus 1 divided by 4 as this expression. You can say 4 times y plus 1 divided by 4 minus 1. That's what we have for the definition of f. And if you simplify this using basic algebra, you'll get y plus 1 minus 1, which is equal to 1. So we find an x, which is y plus 1 divided by 4, such that f of x is equal to y. So we have successfully proved that f is an onto function. Why? Because it covers all the members of the codomain, which is a set of real numbers. Now let's disprove part B. I'm going to show you that part B, which is function h, is not onto. How can I do this? I use a counterexample. So we say the codomain of h is Z, right? Because both the domain and codomains are Z. That's what we showed here. That's what we defined here. So we know that 0 belongs to the set of integers, right? 0 is an integer. So that's why 0 is a member of the codomain. However, you cannot find any integer such that h of n is 0. Why? Because in this case, if h of n is 0, it means that 4n minus 1 is 0, correct? Because the definition of h of n is 4n minus 1. So if 4n minus 1 is 0, it means that 4n is 1 and n is 1 divided by 4. But we know that 1 divided by 4 is a quotient and it's not an integer. So there is no integer like n such that f of n is 0. Basically, we can say f cannot cover 0, which is an element in the codomain. that's our counterexample. Why? Because if f covers 0, then 4n minus 1 should be 0. You know, we are using a proof by contradiction. We say, okay, so if 0 is covered, so 4n minus 1 should be 0, and then 4n should be 1, and then n should be 1 over 4, which means that you know, 1 over 4 is an integer. Why? Because the domain of H is also the set of all integers. But we all know that 1 over 4 is not an integer, and that's why we can conclude that there is no integer like n such that f of n is 0, and 0 is not covered by function f, and that's why f is not an onto function. Alright, so after defining one-to-one and onto functions, we have a very interesting definition. We say let f be a function, f with the domain x and codomain y, be a one-to-one function, one-to-one correspondence. One-to-one correspondence means f is one-to-one and onto. That's a new term that you need to remember. When we say a function is a one-to-one correspondence, we mean that f is both one-to-one and onto. Okay, so please remember this. So if f is both one-to-one and onto, then there is a function which we call it f inverse with the domain y and codomain x. So please note that in f, x was a domain. In f inverse, x is a codomain. In f, y was a codomain, but y here is the domain of f inverse. So we say there is a new function called f inverse such that is defined in this way. For every element y in the domain of f inverse, which is y, f inverse of y is defined as the unique element in set x such that f of x equals y. So basically, if f maps from x to y, f inverse is a function that maps from y to x, right? So that's called the inverse of a function. We call f inverse the inverse of function f, and if you want to define it formally, you can say f inverse of y is x if and only if y is f of x, right? So we replace y by x and x by y. So f inverse of y is x means that y is f of x. Basically, here this y is the same as this y, and this x is the same as this x. So if f of x is y, then f inverse of y is x. And if f inverse of y is x, we can conclude that y is f of x. So let's see this diagram that shows the concept of a function's inverse. Basically, the arrow to the right shows function f, and the arrows to the left shows the inverse function of f. So if this element of the domain x is mapped to this domain of the codomain y, then the f inverse maps in the opposite direction, maps the same element of the codomain to the same element of the domain, correct? So when f maps x to y, f inverse maps y to the same x. So the direction of the mapping is the opposite for a function and its inverse. Finally, we define two sets with the same cardinality using the concept of one-to-one correspondence and one-to-one and onto functions. You remember that we previously defined the cardinality of a set as basically the size of that set or the number of elements that are in a set. So here we are going to define it more precisely using the concept of functions. We say let A and B are any two sets. We say A has the same cardinality as B if and only if there is a one-to-one correspondence from A to B. Or in other words, A has the same cardinality as B if and only if there is a function f from A to B that is both one-to-one and onto, correct? So this is a very simple definition for two sets with the same cardinality. Now let's extend this definition to a countable definition. We say a set is called countable infinite if and only if it has the same cardinality as the set of positive integers z plus. Okay, so we call a set countably infinite, okay, if and only if it has the same cardinality with the set of positive integers z plus. Or in other words, if and only if we can find a function that is both onto and one-to-one and maps the set A to the set of positive integers z plus. Okay, and the rest of the definition says a set is called countable if and only if it is finite or countably infinite. So the set is called countable if it is either finite or countably infinite. It's obvious that if a set is finite, you can count the elements of that set, right? So the first part of this definition is easy. Obviously, if a set is finite, it is countable. But it says if it is countable if it is finite or countably infinite. What was countably infinite? It means that that set has a one-to-one correspondence to the set of positive integers z plus, correct? And obviously a set that is not countable is called uncountable. So an uncountable set should be both infinite and not countably infinite. So if a set is finite, it's obviously not uncountable, or it's obviously countable, correct? Now let's see an example from the book regarding the countability of an infinite set called Z, which is a set of all integers. We are going to prove that the set of all integers is countably infinite, correct? So in order to prove that Z is countably infinite, we need to give an example of a function that is both one-to-one and onto and maps the set of Z plus into the set Z, correct? In this case, we can simply say we have proved that Z is countable. So here is that function. Function f of n equal to n divided by 2 if n is an even positive integer and negative n minus 2 divided by 2 if n is an odd positive integer. So this function f of n is a one-to-one and onto function. I will ask you later to prove that this function is both one-to-one and onto, but in order to give you a sense of this function basically maps all the even positive integers to the set of positive integers and also maps all the odd positive integers to the set of negative integers. So this way you can prove that the cardinality of z plus, which is a set of all positive integers, is equal to the cardinality of z. So please note that z plus is a subset of z, so it looks like that z plus is a smaller set, but based on this definition right here, we prove that z plus and z has the same cardinality, or in an intuitive way, you can say the element of z plus is equal to the number of elements in z plus is equal to the number of elements in z. That looks very, very interesting because we obviously know that the element of z plus is the number of elements in z plus is half of the number of elements in z, because z covers both positive and negative integers, but z plus only covers positive integers. But here we showed that z and z plus have the same cardinality, so that's a very interesting observation regarding the cardinalities of z plus and z.